In this video, we are going to be talking about the periodic trends and the rationale behind it. So before we talk about the actual trends, let's talk about why the trends exist. So on this slide, we have lithium and fluorine, as well as sodium and chlorine. Lithium and fluorine are located in the same row, versus lithium and sodium are in the same column, as are fluorine and chlorine being in the same column. So it's nice to be able to compare these four atoms, because we generally look at trends either within the same row or within the same column on the periodic table. So lithium has 3 protons in its nucleus, so it essentially has a +3 charge, versus fluorine has 9 protons, so it has a +9 charge. So the amount of positive charge coming out of the nucleus is 3 times stronger for fluorine as it is for lithium. Lithium has 2 electrons in the inner shell, as does fluorine. That's the first energy level. They both have 2 electrons. We're going to ignore that because those inner level electrons aren't changing, therefore they aren't a factor as you go across the periodic table. However, the valence electrons, or those outer shell highest energy level electrons, are changing. We have 1 for lithium, and we have 7 for fluorine on the second energy level. So we have 7 X's, if you will. So if atoms are like magnets, electrons and protons are the opposite ends of the magnet. They will attract each other because they have opposite charges, just like the north and south end of a magnet. So here we have a +3 charge being attracted to the 1 electron in the outer energy level. And it is attracted to that electron, and that's what helps hold the electron in, is the positive charge coming out of the nucleus. However, as we go across the periodic table to fluorine, the amount of positive charge coming out of the nucleus has increased 3 times the amount, as well as the amount of negative charges in that outer energy level has also increased. Now it's 7 times as strong. So our magnet, if you will, is much stronger over here. The positive and the negative attraction charges are much stronger here, and it actually pulls the electrons in closer to the nucleus. This results in smaller atoms. It results in electrons being held more tightly to the nucleus and harder to get rid of. Fluorine really holds on to these electrons when compared to lithium. And that is the explanation for the trend whenever you go across the periodic table. You'll notice quickly looking at sodium and chlorine that it's the same deal. The number of inner electrons stays the same going across the row, but the number of outer electrons as well as the number of protons increases dramatically going across, making chlorine a smaller atom than sodium due to that higher level of attraction. Alright, so going down the periodic table, we're going to look at lithium and sodium. There are 2 factors here. One is the size of the atom. The atom gets bigger as we go from lithium to sodium. A big reason as to why the atom is getting bigger is due to what's called a shielding effect. Basically, lithium has 2 electrons on its inner energy level and 1 on its outer energy level. These 2 electrons that are located on the inner energy level, it's kind of a tongue twister, have a negative charge just like this one. So if you put the north end of a magnet next to the north end of a magnet, it repels. Obviously these electrons do the same thing. So this electron is attracted to this positive nucleus, and it is somewhat repelled by these negative electrons. But it's still definitely attracted to that positive nucleus. Going down to sodium, sodium has 1 electron in its outer energy level as well, but it's on the 3rd energy level. Now it has 10 electrons on its inner energy level, so it has 8 on the second one, and it has 2 on the first energy level. And it does have a +11 charge. It says plus 11. It's kind of hard to read. But the big thing that's important here is that these 10 electrons all have a negative charge, and this one electron is attracted to those protons in the middle, but it's really being blocked by all of these other negative electrons, and it causes it to not be attracted as strongly. It's called a shielding effect. This is what causes sodium to be bigger than lithium. That and the fact that the electron is being put in the third energy level, so it's a higher amount of energy. It's a bit further away from the nucleus than the second energy levels. So as you go down the periodic table, atoms get bigger because electrons are being placed in energy levels that are further and further away from the nucleus, as well as due to this shielding effect, all these other electrons which kind of block the valence electrons from truly getting at the nucleus. So as we look at lithium to sodium, sodium's valence electron is not held as tightly as lithium's due to the shielding effect, as well as due to being further away from the nucleus. This causes sodium to lose this electron much easier than lithium's losing that electron. In that trend going down the periodic table, the trends going down the periodic table are all explained with those two reasons. We could talk about chlorine and fluorine, but if you look, it's the same idea. We have two inner shells here, two inner electrons here, and here we have 10, so the same over here. And chlorine's valence electrons are also being put in the third energy level. So further away, more shielding. So the same ideas. So atomic size. I'm going to draw the arrows as far as increasing size. So atoms get bigger as we go down the periodic table, and they get bigger this way. So if I was to draw one main arrow, I would draw an up diagonal arrow like this. And the reasons for these can be, well, we just went through them on the previous slide. Going across, it has to do with the positive charge increasing in the nucleus and the number of valence electrons increasing that are the same distance away from the positive nucleus, as well as the fact that the number of inner electrons remains the same. Going down the periodic table, atoms get bigger because electrons are being placed in higher energy levels, which are for the most part located further away from the nucleus, as well as the number of inner electrons are increasing, causing a shielding effect from the nucleus. Alright, the trends for ionization energy and electronegativity are the same. Meaning it's a general trend this way for both. So it increases going up and over. And ionization energy and electronegativity essentially get at the same thing. Ionization energy is how much energy it takes to remove an electron from an atom. So the more energy it takes, the less likely it is to happen. So helium, for example, would have the highest ionization energy due to the fact that it is the smallest atom. Its valence electrons are closest to the nucleus, and they are being pulled in pretty tightly. It would take a lot of energy to remove an electron from helium compared to any of the others on the periodic table. Electronegativity is the likelihood of an atom to gain an electron from a different atom when it's bonding. This is an actual lab calculated value versus this is a scale defined from 0 to 4 on how likely an atom is to take an electron. So these two kind of get at the same thing. If it's really hard for an atom, unlikely for an atom to lose an electron, it has a high ionization energy, it's going to be really likely that it's going to take an electron when it's bonding. So fluorine is right here, and fluorine has the highest electronegativity because of the same reasons it would have a really high ionization energy. It's a small atom, and its valence electrons are being pulled in pretty tightly to its nucleus. And fluorine does have the highest electronegativity. It is the most likely, it's the highest likelihood atom of taking an electron. We aren't including the noble gases, column 18, at all in for electronegativity, because these are relatively stable atoms and they are not involved in bonding, and electronegativity is talking specifically about bonding versus ionization energy, which is not talking specifically to bonding. So that's why we cross it off for electronegativity. Alright, we have one more trend. Reactivity, there are actually two opposite trends. It depends on whether an atom is a metal or a non-metal. And it tells you how reactive an atom is when compared to another atom. And we'd always compare a non-metal atom to another non-metal atom, or a metal atom to another metal atom. It wouldn't be fair to ask you a metal atom versus a non-metal atom. So we need to draw our staircase in, because our nonmetals are located over here, as well as we're going to cross out the noble gases again, because those guys are unreactive. So as far as reactivity, these nonmetals take electrons. So we want to pick an atom that is small, where the electron is going to be pulled in tightly to its nucleus. It's going to be relatively close to the nucleus. And that would mean that the trend needs to go this way, where X is fluorine once again, and it is the most reactive nonmetal on the periodic table due to that small atomic size. For metals, metals give up electrons for the most part. So we need to pick an atom that's big, because its valence electrons are far away, relatively speaking, from the nucleus, and relatively easy to take. So we want to pick the biggest atom as far as metals are concerned. So we are going to draw our arrow this way, with francium being the most reactive metal on the periodic table. And that is it for our periodic trends.